Today we will talk about fuel cells, structure of fuel cells. You have already learned that the main components of a fuel cell are an electrolyte sandwiched between two electrodes where oxidation and reduction occurs. The current travels through an outer circuit producing electricity and ions go through the electrolyte. We will go to a bit more detail today. All these processes are actually quite complex. Many reactions are occurring. For example, gas transport or gas tightness for the electrolyte case. You need ion conduction. You need electron conduction. For some components, you need isolations. There will be catalytic reactions, surface reactions, transport, adsorption, desorption. So quite a complex network of processes. When we start with the electrolyte, it was already mentioned several times. It has to be gas tight or tight for the fuel and the air side. It has to be ion conducting and it has to be an electrical insulator, otherwise we could not extract electricity. And this is illustrated in these small cartoons. So we have an ion, and this depends on the type of fuel cell you are working with, and we come back to that. And you need to have a tightness for the fuel and the air, and you should be isolating for electrons. When we then go to the cathode side, of course there has to be some catalytic activity for the reduction reaction. Gas transport or transport of air has to be possible, for example through porosity. Electrons and ions need to be conducted. This can be illustrated here. This is a very general example. It just shows that you have several phases involved in this process. A phase that conducts electrons, one that conducts ions, and one that provides the fuel. And that can be 3 different phases, but it must not be different phases. And the same actually is also true for the anode side. You need some catalytic activity. Again, you need also gas transport, electron and ion conduction. And the same illustration goes also for the anode side. I will now present the detailed reactions for the different fuel cell types. They are listed here in this table, and the colors are for better distinction later on. So as you know, the fuel cell types are divided according to the nature of the electrolyte. We have alkaline, AFCs, polymer exchange membrane fuel cells with a polymer membrane electrolyte. We have phosphoric acid fuel cells, solid oxide fuel cells, and molten carbonate fuel cells. I will not come into detail into the sub-versions that also have been developed. They will come later in the specific sections. The electrolyte nature also determines what kind of ion you have to transport through the electrolyte. It also, of course, here are the examples of the chemical composition of the typical electrolytes for these types. And these determine in which temperature range the fuel cell is working and also which type of fuels you can use to produce electricity, including which efficiency you can achieve. I will go to a little bit into detail for the single types now and show you the overall reactions and some of the materials, typical materials. Let's start with the alkaline fuel cell shown here. And this is again the sketch of the 3 main parts, the electrolyte and the cathode and anode. You see that here in this case hydrogen as a fuel is taking up hydroxide ions by donating or releasing electrons. And the hydroxide ions, they come from the cathode side. So they are the traveling species through the electrolyte. The overall reaction is the well-known reaction of hydrogen, oxygen to give steam. The typical materials involved in alkaline fuel cells are shown here. We have on the electrode side carbon Teflon materials and not noble metals as catalytic active parts. When we go to the fuel cell types which involve proton transport through the electrolyte, these are the PEM fuel cell and the phosphoric acid fuel cell. You see here that the elementary steps are slightly different. So at this time we have the oxidation of hydrogen in the anode, releasing electrons and protons, and in this case the protons travel through the electrolyte to the other side, where they react with oxygen to form water. The overall reaction is still the same as in the previous case. For the two types of fuel cells, here the typical materials are listed, for phosphoric acid fuel cell and also for the PEM fuel cell. We move now to the solid oxide fuel cell. Here the main reactions are listed. Again, a slight twist. On the anode side, hydrogen reacts with O2- to form water and release electrons, and the oxygen ions, they come from the cathode side through the reduction of oxygen. So in this case we have O2- being transported through the electrolyte. The overall reaction is again hydrogen and oxygen give steam. In addition to that, also carbon monoxide can be used as a fuel and react in the same way with oxygen to give CO2. Why is carbon monoxide now interesting? Actually, this is a product of the reforming or partial oxidation reaction of hydrocarbons. And that way this fuel cell can also utilize hydrocarbon fuels such as natural gas or biogas. The involved materials for the electrodes are listed here. They're all non-noble metals or oxide structures that are being used for the cathode and anode side. And the final type of fuel cell in this row is the molten carbonate fuel cell. In fact, here we have similar overall reactions as in the case of the solid oxide fuel cell. However, the traveling ion through the electrolyte are carbonate species. And that also means that you have hydrogen reacting with carbonate to release steam and CO2 and electrons. So a bit more complex reaction with more reactants and products involved. As you see, also the overall reactions are the same. Hydrogen or CO react to release steam and CO2. So also molten carbonate fuel cells can use hydrocarbons as direct fuel. The involved materials are listed here in this table for the electrodes. Also non-noble nickel-based electrodes materials. So this concludes the how the single reactions occur in the different types of fuel cells. You see the type not only determines operating conditions, materials, it determines which fuel can be used and also which elementary steps occur and the transport mechanisms through the electrolyte. So there are a lot of variations in the details for the different types of fuel cells. I would like to conclude with a few examples to show you that there are actually commercial or pre-commercial products out in the world that utilize these different types of fuel cells, and you can go to the homepages of the different companies to learn more details about the Alkaline fuel cell. There is here a stationary application as an example. For the PEM fuel cell, I selected a hybrid car with a battery fuel cell vehicle, Toyota Mirai. For the phosphoric acid and all the other fuel cell types, I also selected some stationary applications. They are not restricted to those. It shows also that there are different sizes we are working with, from smaller to large scale, from a few 100 watts to the hundreds of kilowatt and even megawatt scale. With that, I would like to conclude this part, structure of fuel cells. Thank you.